Hello, students. We're going to go over these extra practice problems from Module 2. This module, well, we started working with data, and so these problems, we have 3 of them, and we will work with 3 different data sets in R and perform some operations to get used to these commands. Here we are in our studio. We have removed all of the saved objects. Well, let me go ahead and set my working directory. And I will go ahead and create an R script. Extra practice module 2.R. I like to start my scripts just like we saw in the last extra practice video by removing all of the saved objects. Now, number one, we are working with the Golub data. Okay, we had a lesson on this, and if you recall, this is inside the library mult test. Well, I probably should run these 2 commands. If you recall, this matrix has 3,051 rows and 38 columns. Each column corresponds to a different patient sample, and then each row corresponds to a different gene, where the entry in the matrix would be the expression level of that gene for that given patient. Well, one thing that we have the command in our Canvas course, so maybe we'll just copy and paste that, was we created this factor, copy and paste, for the 2 different subtypes of tumor. So here, this acute lymphoblastic leukemia, we now have labeled ALL rather than the 0, and the acute myeloid leukemia we now have labeled as AML rather than the 1. A and B, we practice writing data to a file. So in letter A, well, let's talk about what we want here. We want only the first 5 rows, the first 5 genes, and only the AML subtype. We will use the write.csv for this. We want to take the first 5 rows of the matrix and then require this factor we just defined to be equal to AML. That is what I'm exporting, and then I need a file name, and we are told it should be AML5.csv. Let me run this and make sure there are no errors. Okay, looks good so far. I did not get an error message, so let's go ahead and do letter B. Well, the 2 things that change here, number 1, we're writing to a text file, so we use write table, and then we want the first 5 rows for the other subtype. So we still are using the first 5 rows, but we require this factor to be the other, so ALL. And then we need to give a file name, which is told to us should be ALL5.txt. Let's run this line. Okay, this is why I ran it. I need 2 equals, and then we will do it again. Wonderful. If you go into your working directory, you will see ALL5.txt and AML5.csv. Letter C, compute the standard deviation of the expression values on the first patient for the 100th to 200th gene. So this is 101 genes in total. Well, standard deviation is this SD, and we want from gene 100 to gene 200 And then the very first patient. Here we have the answer, 0.9174976. Letter D, compute the standard deviation of the expression values for every gene across all patients. This is lowercase all, meaning all 38 patients. Find the number of genes with standard deviation greater than 1. Well, let's read the first sentence again. We want the standard deviation of every gene. So we are performing this SD across, well, for every gene. So for each row, we may use the apply command. We want to apply to the matrix Golub, well, across all rows, standard deviation. Well, let's just see what happens when I run this. Okay, well, that's very large. Maybe I should save this as a variable. In fact, we know it would be large because we have 3,051 rows. So we have 3,051 standard deviations. So let me just save this into a variable, which I am calling gene SD. Now, what else do we need to do here? We want the number of genes that have standard deviation greater than 1. So what happens? Maybe let's run this and then we can experiment to see how I'm going to do this. If I ask gene SD bigger than 1, you see this is a vector of the same length, and it either gives true if the standard deviation of that gene is bigger than 1, or false if the standard deviation of that gene is less than 1. So how can I figure out how many entries of this vector are true? Well, let's go back to something that we discussed. Well, it came up as one of the short answer in our first practice problems. Remember we made this vector V, which was C of 5, true, and vector V itself was the vector 5, 1. In fact, 5 is numeric, and we know a vector can only take in one type, and so the true was forced to be 1. Now, if I go up and just ask for, say, the class of this vector, it will not be numeric. You see, it's logical. But if I try to apply a command like sum, I get a number. In fact, I think this is the answer to my question, but let's make some sense of this on a smaller example. So now let me ask to sum something that has true, false, false, true, and true. You see, I have 3. So when the logical expression true or the logical expression false is coerced to being numeric, true will have the value 1, false will have the value 0. So this, I know the answer, 123, and I can use the sum command. So let's sum, and this will give me the answer to letter D. Letter E, we want to plot the 101st gene against the 102nd gene in a scatter plot. And in this one, we're going to need to use the Golub.g names for the first time, well, in these extra practice problems. So before I start typing my plot commands, let us remember what this Golub.g names. Well, for instance, what is the 101st row look like? Well, there's 3 entries that have different naming convention, but you notice the name is here. It's the second entry of this row. And similarly, if we just ask for the 102nd, the name is here. It's the second entry of this row. So now let's start typing our plot command. We want to plot, well, we want to plot the 101st row against the 102nd row. The labeling, that's what we started off thinking about. So we want golub.gnames 101 row and the second entry. That will be my X label, and then the Y label, we want golub.gnames 102nd row and the second entry. Okay, let's run this and cross our fingers that we didn't make a mistake typing. It looks great. So let's just save this. Move on to number 2. Here we want to use the capital ALL data set. It's in the capital ALL library. Okay, the question is, have you installed this or not? This library is part of Bioconductor. I already have it installed, but if you have not installed it, you want to use this BioCManager command. So I have entered this command, but we must first call library all and then data all, just like we did with the last data set. And then this is the command that is given to us in our extra practice problems. If you're interested in seeing what this looks like, what do we have? Well, you see the rows correspond to different genes. And then, well, how many columns do we have? We have 19 columns. So there are 19 patients in this disease stage. All right, so first question. Well, we want a histogram. We can just type hist. You might wonder what you're looking at here. Well, the values in this B1X are all expression levels. For example, we could ask the min. It's about 1.98, close to 2, and we could ask the max. It's a little over 14, and that's what you see down here. So what this is plotting is across all of these 19 patients and the 12,625 genes. It's plotting the frequency of the gene expression values that you see across the bottom. So one thing I should do is include this histogram command in my script. Next question. Compute the mean gene expression for every gene over these B1 patients. Well, we already realized that the genes correspond to the rows. So as we saw in the last example, we want to use the apply function. We want to use this B1X. And then across rows, we want mean. If you just run this, it's a big vector where we have averaged across all the rows. So maybe I should just save this into a variable. Say we were handing this in, which as usual, these extra practice problems we do not hand in. However, you will be handing in assignments. We do not want to print out this huge vector, but we would print out this command into our work, and then we would also be able to answer this next question. So the next question, letter C, says the following. We want the gene identifiers of the 3 genes with the largest mean. Okay, let's define O. This will be my new indexing set. We want this in a decreasing fashion. Well, what is this O? Maybe I can just show the first few entries of it. Well, this is our new indices. In particular, it says the 12,586 gene has the highest average expression, and the 1,979th gene has the next highest average expression across this B1 that we are working with. So what I want here, maybe I'll go up to my R script. I want B1 mean, I want the first 3 genes. This would be O. Let's run this. Well, what we're looking at, here are the identifiers, 1, 2, and 3. Okay, let us move on. We have one more question. So at this point, we move on to number 3, and you notice we're no longer using the capital A, capital L data. We can remove all of the saved objects, except we are on number 3. We want to use trees data. So let's call that. Here we just want to produce a figure, and we want 2 overlaid scatter plots. We want girth to be on the x-axis. We want one to be girth on the x, height on the y, and we want one to be girth on the x, volume on the y. And then we're told some information about how to make the symbols and colors. Well, we briefly used this data set in one of our lesson overviews, but you can see it's a data frame, 31 observations on 3 variables. Okay, well, the nice thing is we can just ask summary to get some information. So the y values in my scatter plot will come from height and will come from volume. Now, this part we have to pay a little bit of attention to. So you notice height ranges from 63 to 87 y values. Volume ranges from 10 to 77 y values. So if I want both of them to show up, maybe I should choose my range of y values to be maybe 10 to 90. That would include both plots. I think also I will use the attach command so that I don't have to use $signs when I'm plotting. So let's attach trees. Now let's use our first plot command. We want to plot girth, that's the x, height, that's the y. We want the color, we are told, to be blue. And then the kind of symbol, we want this plus. Well, so that I can put both plots together, and we discussed this, we want our y limits to be 10 and 90. And then maybe I'll also label. Height and volume. This is for the whole plot. We will see both the height and the volume. All right, let's run this. It looks great so far. Now, don't use the same command because that would generate a new plot. What we want to do is add points to this. So here we want still girth on the x. We want volume on the y. We want the color be red. And then we want this O. Oh, so you notice my color was black, and you can see where my error is in the command, COL, rather than the word color. So let's run it again. Oh, now it looks really nice. Well, my plot is as directed. If I want to be a little fancy, I could add this legend at the bottom right. So let's run this. And here it has appeared. Well, let us save this. What I will do, just as I did in the first extra practice problems video, is I will create a file which has my code, my answers, and then the images, and I will put that on Canvas for you together with this .r file. Well, thank you so much.